In this problem, we have a single effect evaporator, and we're trying to concentrate a solution of sugar dissolved in water. And so what I want to do first, I have a diagram. I'm going to pause and just label the diagram, and that's always a good thing to have everything clear so we know what notation we're using, and then we'll look at how to go about solving this problem. So I've created notation where m dot is a mass flow rate, so we're going to need to determine the mass flow rate of the vapor leaving, feed mass flow rate of the sugar solution, and the steam mass flow rate. Now, in order to determine the heat transfer, we're going to need to know the temperature of the liquid in the evaporator, and since it's not pure water, we want to see how big a correction we have for the fact we have sugar dissolved in the water. So the mass fraction of the sugar is 0.80. However, what's important for calculating the boiling point elevation is the mole fraction, and that's much smaller because sugar has a much higher molecular weight than water, so it's more in the order of magnitude smaller. So if I go to the steam tables, and basically I'm using Raoult's law, assuming pretty close to ideal solution, particularly this mole fraction, and so the mole fraction of water would be 1 minus the mole fraction of the sugar solution times the saturation pressure of water. That's going to be the 1 bar pressure in our system. If I use the steam tables to calculate this, so saturation pressure is going to be 1 over 1 minus 0.0046, I get a saturation temperature of 99.73 degrees C. So that's what we'll use for the heat transfer. So the first step then is calculating the rate of heat transfer. So Q dot is the rate of heat transfer. It's the heat transfer coefficient, the area for heat transfer, then the temperature of the steam that's heating it, minus the temperature in the evaporator, which we just calculated is 99.73. So let me pause and substitute these numbers. So that's the heat transfer rate, 4,510 kilojoules per second. Now, heat is transferred by condensing the steam that's fed in 140 degrees. So the mass flow rate of the steam times the heat of vaporization has to equal 4,510 kilojoules per second, and so that's the mass flow rate of steam. And then again, steam tables at 140 degrees, I can find the heat of vaporization, the enthalpy of vaporization per kilogram, and this means I can solve for the mass flow rate of steam. That's 2.10 kilograms per second. So that's one of the values we were trying to solve for in this problem. Next, we need to do mass balances in order to determine the mass flow rate of the feed. And mass flow rate of the feed, well, the liquid that comes in either leaves as vapor or it leaves as the liquid at the bottom, so that's the overall mass balance. And then the mass balance on the sugar is mass balance times the mass fraction of sugar in the feed, so X is mass fraction of sugar, and that's going to be, since all the sugar leaves in the liquid phase, that's the mass fraction of sugar in the liquid phase. So this is 0.05 and this is 0.08. Give us a little more room here. So the mass balance of the liquid, mass flow rate of the liquid, is related to mass flow rate of the feed, which means then mass flow rate of the vapor is 1 minus 0.625 times the mass flow rate of the feed. Now that we have these mass balances, what we need to do is an energy balance on the evaporator. And so the heat that we add, Q dot, is distributed. We think of the mass flow rate coming in as being broken into 2 parts. Some of it is going to end up as liquid at a different temperature, and so the enthalpy of that liquid at 99.73 minus the enthalpy of the feed, these are per kilogram, that's one of the terms, and then the rest, water that evaporates, well, the enthalpy of that water at 99.73 minus it came in the feed as a liquid, so the energy to evaporate it is there. And so let me pause. All I'm going to do is go to the steam tables, look up the values, and I'll make some notation to make it clear where they come from. So let me pause and do that. So I've indicated the temperatures that we use When we go to the steam tables, I've substituted in the values. The only unknown now in the equation is the mass flow rate of the feed. So that means we can just solve this for the mass flow rate of the feed. And so 4510 is going to be equal minus, because we're bringing in the liquid at a higher temperature than it's leaving. And then this term is plus mass flow rate of the feed. So that means we can solve for the mass flow rate of the feed. So let me add these together first. And so then mass flow rate of the feed, 5.62 kilograms per second. Again, that's one of the values we wanted to determine. We're almost finished here. The last thing then we need to calculate is the steam economy. So to do that, to calculate the steam economy, we're going to need the mass flow rate of the vapor leaving, and that's, as we determined for the mass balance above, 0.375 times the mass flow rate of the feed. Okay, so steam economy then is how much we evaporate over how much steam we feed in that condenses. So you can see the steam economy is essentially 1. We get some benefit because the liquid feeds at a higher temperature than in the evaporator, and then of course heat's vaporization are a function of temperature. So you can see, of course, for a single effect, this just says that we're using steam as efficiently as we could. If we have multiple effects, then this steam economy could be greater than 1.